Today's topic is an interesting topic. We are going to change track now and go deeper into the subject. In particular, we are going to start talking about a framework that has gained a lot of attention these days. This framework is called Ray, which is interesting. Obviously, the term is quite positive. I'm just looking out of support vectors here. The last of the ray of light is disappearing. So it's a little bit paradoxical that we start discussing ray when all rays of light are now vanishing. Let's see. So I will use this as a context to discuss a broader topic, that of distributed computing. And what is distributed computing? If you understand the core concerns of distributed computing framework, you will understand the basic ideas of Ray. Otherwise, it's hard to understand why exactly the Ray API or Ray framework. What's the big deal about the Ray framework? I keep hearing this, by the way. And this is very real. I just had somebody call me last week and said, I wrote my own complete framework of functions and decorators and everything, and it seems to be able to do everything that Ray does. I wrapped up VLLM with it, and I wrapped up Olama with it and could do it. And obviously, when you start asking, if you go into a Socratic mode and start asking questions, the developer, who's actually extraordinarily smart, realized that he might have missed the point of distributed computing altogether. And he realized why such frameworks are needed. Now, we speak of the word distributed computing. Let's start with the idea. Why do we need distributed computing? And what is distributed computing? See, everything we do in software is driven by hardware considerations. Always remember, if hardware architecture changes, the way we write software has to fundamentally change. It is something that if you have been doing computer science courses, Hennessy Patterson's classic computer architecture textbook, it's a deep lesson to learn that everything is about optimization or exploiting the hardware architecture to its maximum. So with that in mind, let us now, I'll pose this question. What is distributed computing? Could one of you explain to me what is distributed computing? Andrew, you have a microphone there. Turn it on and bring it close to you.
I'm on the Zoom.
No, not on the Zoom, not on the Zoom. No. And pull it towards you. Yeah.
Distributed computing, I think, is when have multiple computers or multiple servers, they run something like them.
And why do you have multiple computers or multiple servers?
To expand the amount of storage, read, and other processing power.
Why not make a ginormous chip? One processor, one memory to rule them all.
I think that's something to reliability as well. If one part of the if the chip fails or some like part of that one computer fails, then the entire
That's right.
Program you can't run it or the data is going to be something. But if on multiple computers, then we only use part of it.
Yes, you hit upon some really good points. Would somebody like to add more color to that? But broadly, yes. Anyone would like to chime in? Anyone at all? We are asking foundational questions. Why distributed computing and what is it? What, why? Aditya, you're smiling. So let's go with it. Turn on your microphone. Yeah,
As in,
well,
I have very similar ideas.
no,
But
no,
I will-
Aditya,
Oh,
press that button.
the switch button.
Hmm.
I
Yeah.
had very similar ideas with ideas, so nothing new, but I think it's more, I'm thinking of like, a parallel example that I can have 100 people working on a project. And, one gigantic person or one, very powerful person working on a project. That may not work out all the time, more number of, hardware in one thing does not mean always like it will end up being more efficient.
Mhm.
The distributed is basically distributing your work across different workers,
Mhm.
and, you can collate their work, and then when it's divide and rule kind of, strategy. You can use that.
Yeah. So that's again a very valid answer. So one close analogy is an anthropomorphic analogy. You take a team of people and they can divide the problem amongst themselves and try to solve it in parallel. But you realize what happens in real life when you build teams. Instead of collaborating, they start conflicting. And coordination of the task becomes so complex that you need program managers and then or project managers, and then you need senior project managers on top of them, and then you need manager of project managers or director of project managers when you have 100 workers. So it becomes hard to tell whether you gained efficiency or not. So why, again, goes back to the thing, why not hire a super duper genius who can do all the work alone? Anyway, guys, come up with ideas. Don't be just passive. There's a
The-
small group of
The
15
super
people.
duper genius will have its downtime, as Andy also mentioned, like it can have, it needs to have its downtime at some point of time.
Yeah.
So in order to,
Mhm.
in order to make sure that your work is continuously being done, there is no, gap in between.
Mhm.
You can't just rely on one, super duper genius. You need the whole team to divide and continuously work.
That is true. That is true. So you guys are all hitting on the right point. I'll give you an understanding from a hardware perspective. See, in hardware, and this is the experience. If you look at the history of hardware, we started out with mainframes. Right? Even in mainframes, we realized that if you, and I'll just do a very high level thing, you could have a CPU. But what is a CPU made up of? It comes from, let's say that it's a CPU that is a chip that comes from a
Screen
wafer.
is not shared.
Oh,
in
I'm
case-
sorry. I'm sorry. I should have. Like I told you today, I'm being very absent-minded. Let's share that. Hopefully, this is better, right?
Yeah.
So the way the world starts out, if you look at the history of things, or how chips are manufactured, you start out with something called a wafer, right? And then you get lots of chips, I, J, K, L, M, etc. chips that you have on the wafer. Then you cut out the wafer, you cut the wafer out into the respective chips. Right? I suppose we know this. It becomes the processing chips. And then what happens is, now one question that is perennially there, that if you have to do a lot of computations that one chip cannot do, that's too much for one chip. If you have a lot of work and some of the work is parallelizable, and that is a crucial thing. The work should be parallelizable. Some work is and some work isn't it? But if the work is parallelizable, then you could argue that you can throw many chips or many processing units to do that. But if you're going to throw many processing units to do that, and the kind of problems that you face are this. You have all of these chips. Suppose you have n chips. how many basically, if this has to send a message to this has to send a message to this has to send a message to this, back and forth, right? And back and forth, you realize that the number of interconnects become quite high. And so people begin to worry that you need some sort of a topology, right? Some sort of a topology. And there are all sorts of topologies, ring topology, this and that, bus topology, some ring buses and whatnot to interconnect these chips. But whenever you introduce interconnects, you realize that you're taking latencies. Data has to move back and forth, right? Partial work has to be shared, moved from chip to chip. So if you look at the history of this field, people have tried to address it in many ways. They have tried to make approach one, make mega chips, like more powerful chips. Let me just say powered, more powerful chips. That has been a successful thing. And that is essentially the Moore's law at chip level. Unfortunately, Moore's law is plateauing. As you know, a chip's compute ability is no more doubling every 18 months. The doubling every 18 months is not taking place, isn't it? So what's the alternative to that? The alternative to that is you put lots of chips together, right? So you put So you make a packaging in which there are more and more so-called cores, isn't it? And sort of these days, all of this core design, multi-core design or chiplet design is pretty common. You keep doing that, isn't it? Now, what happens is if you package it all in a box, you still can have a very high bandwidth bus going between them. Does that make sense, guys? You have created a unit, a shippable, a packaging unit, which you can buy in the market. So for example, today, if you were to go and buy, let's say, Epic 9100 series, what are you buying? You're buying a chip that internally, a packaging that contains practically 100 or so, 100 give or take, little chips or little cores in there. Okay? So that's one way of still continuing to scale up your computation. You can say that your compute power is doubling because you're adding lots and lots of chips inside it. The problem that happens is that you cannot, people used to do that. They used to try and create mainframes in which what is today done inside one of their server processors, people try to do it on a ginormous scale. They would try to do mainframe architectures with lots and lots of these compute units and very expensive interconnects in between them. That was scaling up. And the asymptotic limits are the mainframes. Mainframes are very much there today. They're having quite a resurgence, especially in the world of AI. But there is a problem with mainframe. And the main problem is that the cost rises exponentially with scale. Are we together? It rises exponentially with scale. So as you make it twice as big, it is often almost 10x more expensive or some exponential factor more expensive for every doubling of scale, a doubling of compute size. So scaling up has never been the thing that has been affordable. The government research labs have mainframes, defense systems have mainframes, and so on and so forth. And many financial institutions use mainframes with great success, and it does work for them. The other paradigm is you say, all right, what we will do is we will just use this units, these processing units, let's say with whatever little chips they have. Okay. And now I'll generalize it to call it just boxes. let me just call it server, though a server is not just one processor, it has multiple processors, but let's just call it a server in simple terms. And you create a box of this. Now, typically, if you buy a server, let's say you go to Dell or Supermicro or something, HP or something like that, and you get, or if you are on a shoestring budget and scrappy, you build your own server, then what happens is, what is the typical price of a server these days for general purpose compute? It will be anywhere between 5K to 40K dollars in terms of dollars, right? It's very affordable. Does that make sense? Servers are very affordable. And what does a server have besides having thing? It will have memory, like as in DDR, memory. It will have storage. It will have its own storage disks associated with each of the servers, right? Here. And let's put some storage here, some storage here, some storage here. These are greens are the storage, and each of them have their own memory. Now comes a problem. Good news is, if you could somehow string these machines together, this inexpensive, what are often called commodity off-the-shelf hardware, right? Commodity off-the-shelf hardware or off-the-shelf commodity hardware, whichever way you say it. The basic idea is these are relatively inexpensive, and you could do your job and run large computes still. You would have a win. The problem that happens is whenever you have a cluster, so now let's take this cluster of these servers. When you have a cluster of these servers, there are many, many things, the problems that come up. First problem is latencies. Because now data has to keep going back and forth in every which way, isn't it? Typically, you would interconnect them. If you're lucky, you might put InfiniBand there, or more generically, you would just put you would put a TCP. Data center grade TCPs these days run pretty fast, actually. They run at 100 Gbps, right? Or even more, like 100 Gbps is becoming the norm. 40 Gbps is being phased out. Or if you are a scrappy little startup like we are, so our data center has actually only 10 Gbps that support vectors. The backbone is 10 Gbps for a server. So you realize that the bandwidth of the CPUs or the machines internally is much higher than that. The processors are running blazing fast and doing computations. So whenever you put information on the wire, information has to be first written onto the wire. It has to be read by the other processor from the wire. It will be read from the network card. From there, the network card will map it to the main memory. From the main memory, it will be lifted into the processor. Do you realize how much cost there is? Latency and attendant compute and transport cost. Cost of partial results, right? Or data movement. The other problem that you have in such an environment, so this kind of an environment is called a distributed system, distributed compute environment. In a distributed compute environment, what else can go wrong? Guys, the other thing can be is not all the servers may be equally powerful. You may have heterogeneous hardware, right? Some nodes slash servers, they're used synonymously, may have more compute or more memory than others. And likewise for storage, they may have different amounts of local storage. Does that make sense, guys? And the next problem that you can have is if failure becomes the norm, what does that mean? Let us say that, and I'll illustrate this with a fact. Suppose you have a machine that has a downtime of 1 day per year. So something or the other goes wrong with that server. Maybe the operating system update or some software update glitches out, it needs to be rebooted, or it needs to be taken offline for service. Right? Now what happens is, when you take a system in which the chances of failure, therefore, is one at any given day, 1/365 probability of failure or downtime is something like this. By failure, it may be deliberately also taking it offline for servicing, whatever. Now, that's a pretty healthy machine that can keep running so well. Let's say that you put it like that. Right? Now, how long will it take before you end up in a situation that at least 2 machines will be down? Can you guess? What's the probability that on a given day, 2 machines, like at what number of machines? So what is the size of the distributed cluster? Will you have a situation that at least 2 machines would be down? Can somebody guess? Guys, everybody is so
No,
quiet.
are you asking out of 6, 2 of them are gone?
Yeah. So suppose the distributed cluster has n nodes.
Okay.
At what size of n do you reach a situation that on a given day, it's likely, it is possible that, I mean, throughout the year, there will be, okay, so let me rephrase it this way. What is the, if you want to make sure that on a given day, only 1 machine at worst goes down, hopefully none of them go down, right? How likely do you have that in this 1 year, you'll have a situation at least once when 2 machines went down? So let me phrase, that's a better way of putting it. At what n are you facing a likely situation? Likely means greater than 50% chance that at least 1 day of the year, 2 machines or more will go down. Can somebody guess? The number is actually surprisingly small. But guys, please throw a number. You don't have to be mathematicians. You can just guess. Maybe 200 machines. Andrew,
I'd say,
around 40. So slow. Okay, so low. Justify it.
The more machines you add, the higher chance at least one of them will fail. Because at 40 machines here, you have, 40 possible things that can fail on any given day.
Right. Sort of close. Anybody else?
180.
180, half of them. Yeah. Okay, I'll give you an intuition. Who would like to go? And so one answer is 180. One answer is 40. Somebody who says, no, my hardware is really good. It won't happen. Right? So anybody wants to go with that claim?
It
So
also it also depends on how you set up your HA, right? So if I am the planning guy, I would have one of the machine in the cluster for a failover. And so if one of them goes down, I'll always have the other machine take over the load. The load distribution is not like basically, yeah, one of them will be on a standby mode, sort of.
Right.
I would design a cluster like that. So even if one of them goes down, out of 365 days,
Mhm.
every day at least one of them goes down. The hope is that I have enough turnaround time to get it down to back to like operating six by next day. Otherwise the whole thing will be defeated. I'm just going with that theory.
No, you're right. Actually, what you mentioned is one of the architectural patterns in distributed computing, high availability, to battle the failure problem. But I'm asking a simpler problem. Don't worry about what measures you take, what patterns you follow to fix it, but just guess at what number of nodes are you in a situation that in the year there will be at least one day when there's quite likely that two of the machines would go down. There's more than 50% chance that two of the machines would be down. So this is actually a number that shocks people when I tell them. It is called, and it is something that mathematicians call it the birthday paradox. A birthday paradox is, so let us say that the machine going down is like the machine having a birthday, right? Now, if you take a social gathering, have you noticed that at surprisingly small groups of people, when they gather, the two of them tend to have the same birthday? You'll find at least a pair which has exactly the same birthday. Amongst relatives, it's very common, right? If you look at your extended family, you'll always find sooner or later a pair of people who have the same birthday. And you realize that in such a small group, oh, wow, we have the same birthday. They get very excited. And a mathematician would smile and say that's more or less inevitable. The number is, I believe, I forget the exact number, but I think it's just 23. At 23 nodes, you already reach a tipping point at which you can have at least two of them going down. So you can realize that if one machine fails in a year, I mean, a machine fails only once a year or needs to be taken down, a typical cluster of, let's say, let's just throw a simple number. Let's say that I have 200 nodes, right? Let's say that you put 1U, huh? So 40 times 5 racks, you make 5 racks. Each rack has approximately 40 1U servers. So they have 200 nodes. Right? At this moment, you realize that you're going to have lots of failures. Now, machines don't just fail that. What happens in these machines is there are many, many things that can fail. There's hard disks. Hard disks are notorious for failing. There are thermal failures. The power supplies fail quite regularly. You make them redundant. Hard disk, you try to make redundant using some form of RAID, right? Or CPUs have thermal failures. They start burning out. Every CPU, from the day it's born, transistors keep blowing out continually. So there's a lot of redundancy built into the CPU. As it ages, at some point it becomes unacceptably low. So once you realize that, the realization comes that failure is the norm. This is it. Then you start thinking about the core issues of distributed computing. See, distributed computing has always been one of the hardest topics. You say, hey, we are not going to scale up. We are going to just take commodity hardware and horizontally put them together. And as we put them together, you realize that scaling doesn't, I mean, the fact that you have a lot of cores because you bought a lot of commodity hardwares, it doesn't mean that you got it all scot-free. It comes with its own baggage. And so a lot of software architecture patterns came to handle the inherent problems of distributed compute. These problems are, again, as we mentioned, heterogeneity of hardware, latencies, failures, they become the norm. And one of the companies that really became very, very successful early on because they started with this mentality that failure is the norm was Google. If you look at the history of Google, they realized that they couldn't do search with like in those days, if you look at Alta Vista, it was using Oracle databases, right? People were using really, really expensive machines, Sun servers and whatnot. And then came Google and they said, no, we're going to use commodity hardware. And if you use commodity hardware, and a lot of it will assume that failure is the norm. Let's build a system that is fault tolerant, inherently fault tolerant. At the same time, it is aware of latency concerns, right? There are, for example, issues in distributed system called the cap theorem. It's an older theorem. Many people argue that the time of it has come and gone, but not quite. But I'll just state it in some form. It always lives on. It is consistency, availability, and partition tolerance. In the world of big data was one of the first realizations of a distributed compute framework, right? And if you remember, the early 2000s were the years of the big data movement. Big data was nothing but distributed and efficient framework for distributed compute. It is still there. We just don't use the word. Distributed computes have not gone away. So what is the cap theorem? Can somebody tell me what is consistency in a distributed system? What is consistency?
Measurable performance?
No, it is not actually. So what consistency speaks for is, if you look at this entire distributed system with all these nodes, and the fact that data is like a thing that somehow permeates. Let's say data is all over the place, right? Around the nodes. Each of the node may have its local data, may have a global data, and so on and so forth. So here is what consistency means. Suppose you have a node A, and let me use a different color, A, and you have a node B. Or let me take B at the other end of it, B. You ask, suppose you just said that, let's take something. Some counter is there, some counter, and you added plus 10, and the request was received by A. Let's say that within the data, there was some counter. Let's say counter is the number of horses. And you are just saying we have bought 10 more horses. Node A received the request, right? Immediately after that, let us say now a read request comes. You ask this question from A, how many horses? So let's say initially the number of horses were 50. How many horses? Right? A. Now, what is the answer from A, B? Right? A, B. Now, or C, let us say C, A, B, C. One of two things can happen. A can say, because A knows initially there were 50 horses and 10 were added. So A will be easy. A will say 60. Does that make sense, guys? A will immediately say 60, isn't it? Do we agree or not?
Yeah.
If the distributed system knew that there were 50 horses and A was informed that 10 horses have been added, A will say, well, 60. Now consider the world. What will B say? Right immediately, you have asked this question. This guy, you have gone to B and asked this question, and you have gone to C to ask this question, right? Or maybe different people have gone to B and C to ask this question, doesn't matter, right? So what will B say? You realize that there would be inherently a propagation delay of information. Information is not going to magically travel. The whole cluster will not immediately become aware that the number now is 60. Does that make sense, guys? Right. So there can be a propagation delay. Now the question is, what do you do in such a situation? Do you allow B to answer a question before it has been informed? Like, so let's say that you ask B and B answers 50 and C also answers 50. Right after that. And after a little while, at time plus 1 unit. And then after a little bit, the information would have propagated and A will say 60, B will say 60, C will say 60. This will happen at time, let's say plus 5 units. It took 5 units of time for the information to propagate through the cluster. Is it making sense, guys? Do you realize what's happening? Now we are facing the realities of hardware, the transmission, the propagation delays, the compute delays, the storage updates, the actual realities that you face in a distributed system. So now what happens? The answer at, let's say that this happened at 5 o'clock, 5 p.m. This was at 5:01 p.m. Obviously, I'm slowing the clock down. I'm talking much bigger. And this happened at 5:05 p.m. Now, which answer is correct? The answer that is correct is obviously this answer, isn't it? Well, there is a third answer that's possible. So here are the scenarios. Let me call it scenario 1, alpha, beta, gamma scenario. See, this is a problem. First, let me state the problem. So you see this problem, right? At beta, at situation, at time 5:01, there is a basic consistency problem in the system. Based on who you answer, who you ask the question, you can get different answers, right? This is called the consistency problem. Consistency problem. The second problem, and we need to have a way to solve it. So one way that you can solve it is one of these two situations. You can say that A, and people have done all of this, two-phase commit, and so on and so forth, three-phase. Lots of theories have evolved over the last so many years, decades. One approach could be A can say, well, the fact that I got 10 more, I'm not going to acknowledge it. It's uncommitted data. I want to hear, I send a message to the entire cluster, and everything in the cluster has to acknowledge that 10 and come back with a message saying, okay. And then A will send a commit message to phase and saying, all right, we are at 10 now. You realize that there's a computational overhead to do that. So till that happens, alpha is consistent and gamma is consistent. You will make a transition straight from alpha to gamma, isn't it? Though the problem that will happen. So does that make sense, guys? The way to have a complete consistent solution is to make a transition from alpha to gamma. Alpha A waits, says, no, wait, I will also keep saying 50. I'm not going to say 60 till everybody agrees it's 60 now, right? So then what happens? A becomes unavailable to give you the latest information about it. In fact, while this two-phase commit or any kind of a methodology you use is used to update the entire cluster, the entire cluster has an availability problem. Guys, are we seeing this? It has a fundamental availability problem. And notice that I formulated this problem using latency, not using the network getting partitioned altogether. Right? People often say that, oh, because the CAP theorem has the partitioning there, they always think it's network partitioning. Actually, a partitioning of the network is just the asymptotic limit of extremely high latency. Right? So imagine that the network itself gets partitioned. Let's take this situation. The network temporarily gets partitioned. Right? So then comes a problem. The problem that you have is you have two networks now, N1, N2. Right after A got the plus 10 horses update, the network got partitioned. So once again, there the problem becomes much more stark. A can either say, I value consistency, and I haven't received updates from B that I cannot even connect to B. Right? There's a network partitioning, and so I cannot answer this question. I cannot update because I will lose consistency. The system will lose consistency. The two networks, the two subnetworks will give different answers. And so what you have to do is you have to maintain some sort of a quorum mechanism that says that the only answer that will survive is the answer that the majority network can give. See, if one node in the system goes down, doesn't mean that the whole network has to stop, right? But you need to have some sort of a quorum mechanism that says, in the case of network partitioning, which subnetwork will continue to function? Common sense says is the majority network, right? So that brings about the problem of partition tolerance. Are we together? You need some mechanism of partition tolerance. Now realize the moment you bring about partition tolerance, you have either availability or consistency. Do you agree with that, guys? Because if you have a subnetwork, N1, N2, you realize that you have a choice either for the two subnetworks to be available or to be consistent. You can't have both. Am I making sense? It's obvious, right? It's obvious. This very common sense, obvious statement has been given the name CAP theorem, though mathematicians would wonder where the proving of this is. The proving is literally by inspection that it happens, right? Now, what I'm arguing is CAP theorem doesn't necessarily mean that the network actually literally gets partitioned, as in one disgruntled employee knows he's been going to be laid off today, goes with a mighty scissor and cuts the network down in the data center, though that is known to happen, right? Or pull some wires. But more realistically, a softer form of partitioning is transient partitioning, which comes when the latency becomes unacceptably large. For whatever reason, there's congestion, there is something, and it can happen. And of course, even without that, the fact remains that in a system that has a propagation delay, you need to worry about consistency versus availability. Different, even data systems. So this becomes even more acute, not just in compute, but in data storage systems. So if you look at data storage systems or there's distributed data stores, and these were often called big data stores. Though the word big data is gradually going out of vogue these days, look at things like Cassandra. versus HBase. Right? HBase, big table. Big table is there in your Google Cloud, right? And Cassandra, can you tell which anyone of you happens to know which of them favor? So you basically have to choose. If you are partition tolerant, and you better be if you're a distributed system, to not be partition tolerant is of course not possible, right? So partition tolerance is there. You have to choose between consistency and availability. The only situation where you don't have to worry about partition tolerance is when you are a single node cluster. Either you are up or you're down, isn't it? But in which case, you have both consistency and availability. So you have both C and A. But in a true distributed system, non-degenerate case, you have to choose between consistency and availability. Now, Cassandra favored availability. It's an eventually consistent system. Right? This is eventually consistent. HBase and Bigtable, etc., they are consistent system, highly consistent system. Systems. And it's in the nature of the architecture how data is stored in the Hadoop system, file system, or Google file system. Are we together? So now what am I trying to say? Why did I digress into distributed systems and so forth? The point is, distributed systems are very hard to reason with, right? So let's now come to this here we talked about from the data perspective. Let's talk in terms of compute perspective. Once again, consider that you have all of these nodes. Suppose you have somebody keeping track of the horses, right? So let's say that here is a guy keeping track of computing with the horses. The horse computer does all sorts of bookkeeping about the horses. And here's something that keeps track of, I don't know, cats manager. And suppose you need to do something that has to deal with horses and cats. Do you realize that you have a problem? You have a problem because when a request comes, you need to route it to this, then information would need to go to this, but it may not want to do that. It may give you back partial results. Then you may have to send it back to cats. Then you may have to return back the result. And so you will have to remember who to send requests to, right? So imagine that here is X, let me make it Y, and you, the driver. Yeah, people typically call you the client, the driver, etc. Suppose you need to do your work by using X, getting result back, calling Y, getting result back. You realize how messy it is and how many calls you have to make, data going back and forth, right? And what if this, again, in a fault tolerant system, what if this goes down? And if this goes down, your horse has actually moved here. Who's going to tell you that horse has gone there? Right? So it's hard to reason about this. Now, already you can say, no, wait a minute. What I can do is I don't need to go there. I'll put especially if you come from, you think in terms of packet forwarding, etc. You say, well, all we need is a lookup table to remember where the horse is. Request will come here. It will automatically get routed to the right thing. What did you just do? You just brought in something that knows where things are located at that given moment and where to route the traffic to. Right? When a call comes for the horse compute, right? So distributed computes, therefore, are hard to reason with, which is why they're one of the hardest things to reason with in computing industry. And frameworks like Spark, like there are many such frameworks, but I'll just limit to Spark and the Ray framework of today, both of which came out of the same Berkeley lab. They have had quite a bit of success because they reason about the complexities of distributed compute very well, and they surface a very simple API, right? What they do is, so here's the perfect goal. You client, to it, the entire distributed system should appear not as a, even though it is made up of all of these nodes, which have interconnects, which have horrible amount of interconnects, right? Networking interconnects, whatnot, things like that, that you can imagine, and you don't care. And all sorts of managers like network, orchestration, node orchestrators. See, you realize that at any given moment, any of the nodes may be dying. And you have to be failure tolerant. If a critical computation was happening on X, you need to, if it doesn't get back with the result, you need to speculatively move it to another compute node. All of these are very hard problems to solve. The goal is, how do we do it in such a way that the client, to it, the entire thing appears as though they are working on a desktop. Almost. Magic desktop. Call it magic desktop. In other words, the magic workstation, almost. It should appear as much as possible like the API they would write on their little, a single program, which is completely blissfully unaware of the distributed nature of the compute framework. If only it could do that, that would be the holy grail, isn't it? Now you think about it, you realize that the creating a distributed systems framework is a very daunting task. You basically say, no matter how much heavy lifting you are doing behind the scenes, to the client, it must appear as though, nothing is happening. There's just one guy doing all the work. Are we together? So for example, suppose there is a function, or there is a let's say that you have a class X, right? And within the class, let us say that you have some state, right? Let us call the state, the most obvious state that we can think of is a count of something, right? And then you have a method called increment, right? I, and then what you do is you say count plus equal to I. Right? I've written it in Python, but we could write it in Java or C or whatever your favorite. Rust these days is fast emerging. Pick your framework, but suppose you have this. Now, what happens is that if there will be an instance of X, right? Let's say that X instance. There could be one or more instances of X, but let's just assume that there's one instance of X. It is sitting here. Somehow, the client should be able to get a reference to X instance, right? And roughly speaking, be able to say increment. It is as though the user has, locally, if you were doing programming, you would say X instance is equal to X. Does this look like normal Python programming, guys? Isn't it? And ideally, you would want a framework that to the client is as simple an API as this, right? And such frameworks are hard to create. This is almost like a sort of a high bar. And every distributed framework, there's always a bit of a leakage. In other words, there's a small trade-off. There's a small compromise that you have to make. Now, the nice thing about Ray framework is, so obviously, I'm skipping over 2 decades of history here, right? I'll skip over Spark which was very good data compute framework, and is even today, it's what is the leading workhorse. Right? Spark was created in a generation at a time which made the optimal use of the hardware architecture as it existed 2 decades ago, right? About 2 decades or 1.5 decades ago. At that time, whatever 15 years ago, whatever was the state of the art in hardware, using the layout, the architecture of that hardware, Spark made a lot of sense. Those were the days still when we had a lot of hard disks and so on and so forth. Fast forward to today. Today, 2 things have happened. Well, times change. 2 things have happened. One is that the workload that is becoming fairly dominant, besides the data workload, Spark is still ruling pretty well. And by the way, Spark is good. I'm not doing injustice to other frameworks. I'm speaking of Spark because I use Spark a lot. But there are other frameworks that do quite a good job, right? Flink, for example, does a very good job, especially for streaming data. And there are other such frameworks which do amazing job with distributed compute. But I'll just use Spark as a proxy for all of them. For data computations, they're very good. But today, 2 things have happened. The machine learning workloads have increased quite a bit. And as machine learning workloads increase, we realize that the underlying hardware that it rests upon is different. The cost structure is different. We use, for example, we started with the assumption that you can use commodity hardware, racks of commodity hardware, and you could do your distributed compute. Well, now you realize that commodity is in the eyes of the beholder. Unless you have a $1 billion lying around in your bank, GPU hardware is anything but commodity hardware. They're expensive. Right? A typical GPU, H100, H200, they're at least their sticker price is in the order of $35,000, $40,000. Right? Gaudi is similarly priced. And even if you do secret deals behind the scene, which are never to be revealed, I would imagine that the price still is in the order of about $20,000, $25,000 per GPU. In a box, in a server, you typically put 4, 8, or sometimes 16 GPUs. Right? 8, let's take 8. We are talking about a machine, a single node now, costing you practically $250,000 at discount, possibly. Right? And so and that is one aspect of it. The other aspect is those machines, they're rather impoverished with respect to memory where it is most needed. See, the memory hierarchy is if you are the CPU, the highest, the most gold standard of memory is the L1, L2, L3 cache. Do we know what those are? Just think of it closer and closer to the actual arithmetic logic unit, the registers. Right? Whatever data is sitting literally inside the CPU is running practically at the speed of the CPU, is accessible at the speed of the CPU, or with divide by 2, like L3 cache, etc. might be a little slower. But nevertheless, this cost is expensive. This is SRAM, expensive cache. Right? Oh, by the way, those of you who are hardware gurus, do correct me if this story has changed, right? And I'm speaking something that is no more true. From here, you have the DDR RAM, right? These days is DDR5 RAM. It goes into the DDR5 RAM. Then you have local storage, SSD. You have remote storage, Are we together? Now, one of the things that has happened is the DDR5 has become plentiful, right? The CPU cost is quite low. Most of you can get a fairly good CPU for a few $100s. Couple of $100 will get you, $500 will get you really a very good CPU. Beyond that, you start reaching points of diminishing returns. Right? The other 500 you can use to buy lots of RAM. Right? So this price is commoditized. And so most of the data intensive distributed system workloads have presumed an architecture that looks like this. Are we together? The node architecture that looks like this. On the other hand, and then on the storage, the gap between local storage and remote storage has been practically wiped out because of two things. The 100 Gbps internet TCP or InfiniBand, both of these have made local and remote storage run at more or less the same speed. Not too different. So that has been one of the breakthroughs in recent years. Nevertheless, this is the framework. This is the mental picture hardware for a data compute jobs, right? Distributed computes that are data related, because you do that with normal CPUs and using normal DDRs. Problem comes when you create ML workloads which look terribly different. What you have is a single node in which the CPU is a little kid in the corner, right? And this vast amount of memory, DDR5, is mostly acting as a freight, like cargo ship, moving data back and forth. That's all it does. And the real sort of prima donnas in this story are these GPUs, right? These GPUs that are sitting there. But the problem with the GPU is quite odd. If you take, for example, a 9100 series EPIC, which is pretty common to use, AMD EPIC processor, it will contain about 126 cores. Like this one will have, let's say if it is a EPIC, it may have 126 cores per CPU. In a typical machine, you put at least 2 CPUs. So put together, they have 128, sorry. So you will have 256 cores. And you will have huge amount of memory. You will have something like minimum, you will put 1 terabytes of memory in anybody with a respectable server, right? That is almost expected for data workloads. But when you look at a GPU workload, the situation of a GPU is entirely different. What is a GPU like? GPU actually contains tiny, much tinier cores, but they are close to 16,000 to 18,000 cores per GPU. Think about that, right? These are all tiny vector processing engines or tensor processing engines. Like they can do matrix multiplications blazingly fast, but that's about all they can do. They don't do for example, a typical like a x86 chip. They don't do speculative execution on a deep pipeline or any of the sophisticated things that a general purpose CPU would do. They're dedicated as math coprocessors, but there are 16 to 18,000 of them there. And here comes the thing that kills everybody. How much memory do they have internally on the GPU, or close to the processors? Proximal memory. Now, memory that is proximal, that it is not too expensive to fetch data from. Can somebody enlighten me? How much memory does a typical GPU have? Andrew,
Gigabytes and for 16 and higher model.
yeah, 8 gigs, 16 gigs, 24 gigs, and 80 gigs to nowadays 128 gigs from AMD, but 80, let's say about 80 gig, 100 gigs, let's say 100 give or take, is on the very, very, very expensive model. Do you realize that, let's say that we get a 4090 or something like that, or A6000, it will have somewhere between 24 GB to 80 GB. If you're talking NVIDIA, you realize that how does it compare to 1000 GB of DDR? Do you see it looks puny? So it's a complete inversion of hardware expectations. The compute nodes are almost infinite. Do you see that? And by the time you put 8 of these together, you realize that you're looking at something like a massive, close to 150,000 cores. That looks insane, right? And yet, the total amount of memory they have is less than the on-machine DDR5, right? So your compute expectations have changed, and therefore the distributed system that you need to craft to optimally use this hardware changes. How many of you, when you were doing your homeworks, came across the dreaded or your favorite error, CUDA out of memory error? How many of you have had nightmares of this in your sleep? Right? Is there anyone here who has not encountered this? You have not?
I set it to CPU.
Oh, so Andrew says he has never encountered it because he does all the computations on the CPU.
I don't have the GPU on.
Yeah, that is one way. That's one way to not have it. So, guys, are you understanding that why people have to do almost a fresh rethink of distributed compute and come up with new frameworks? So, new frameworks are emerging, and so that is the context of a framework. That is the Ray framework. I'm not arguing that this is necessarily the best framework. And it has its faults, by the way. It is by no means a very mature framework like Spark. It's very fluid, changes are happening all the time. It has imperfections, it has bugs, it comes with its problems. But guess what? It works enough that a lot of people are using it in production now.
So Asif, one question here.
Yeah.
If we have a single GPU, still a Ray framework is worth because there are 16,000 cores in it. Is that what you're saying?
No, what I'm saying is,
no, my question is because you have put 16,000 cores per GPU, and if you have only one GPU, will Ray framework still be applicable there?
Yes, for one reason. So I'll give you a simple reason. See, what happens is that when memory is so small, right, you need something to throttle down and batch the. So here's the thing. Here's your GPU. You can do without Ray framework. If you have a single GPU, you don't need a Ray framework, but there are certain things that come free with Ray framework that still make it attractive for a single GPU. What is that? See, data, you have a model here loaded. It has used some part of your GPU memory, right? So imagine that you have a 7B model at 8. Like, let's say that you have it at 16-bit quantization. I will just take it as that. 16-bit quantization, right? Which means that almost clean, complete model. This occupies about 16 GB VRAM, video RAM. This is VRAM. Now what happens? every time you start sending in data, that data has to be loaded into the system, right? Every compute creates its temporary data states, right? And this is literally the amount of data. So data states that get created. See what happened. Actually, this won't work. Let's reduce it down to 8-bit. Actually, if you run it at 16-bit, it will fail immediately. So about 8 GB is this. Now, that is for the weights. Remember, these are the weights and biases. Let me just use weights. So if 7B weights are there, they take 7 GB. Now, the derivative of the loss with respect to the weight also exists for each of the weights I exists. That will take another 7 GB, right? And it turns out that we take the quadratic term also, quadratic derivative also. That will take another, if you're using the Adam W optimizer, that will take another 7G, comes to 21 GB, add some overhead, right? A good rule of overhead is 1.2 multiplied by 1.2. So that comes to 23 GB, give or take, 23 and some. What it means is, how much space does it leave for data to, like, it can take only so much data, batch of data at a time. If you shove too many requests through it, you'll immediately have out of memory because there is no space for more data into this. So what you need is guard this GPU with basically a queue. And in the queue, what do you want to do? Suppose every request comes. You need something that knows what is the optimal batch size. Let's say that the optimal batch size is this much. It knows that this much can go through the GPU and it won't have an out of memory error. You need essentially a scheduler that will inspect the queue. If it finds that in the queue at any given moment there are only 3 items, it will take all 3 items or just 2 items. It will take whatever it is and shove it through the GPU. On the other hand, if it finds more than 4 items in the queue, it will pick only 4 items, batch it, pass it through the GPU, through the model, and produce the inference. Right? Oh, by the way, not inference, this is the training. Use it for at this moment, we are training the model. That's why we are using all this training, right? We are training a 7 billion parameter model, right? That's why we need the gradients and the quadratics. It will control your batch thing going through. You need a framework to do that. Typically, what you can do is you can handwrite such a framework, control. So when we write a PyTorch code, you remember your basic loop is for epochs, for mini batch, in data, the inner loop, right? Forward pass, for X mini batch, forward X, loss compute, gradient of loss, backprop of the gradients, and then gradient descent step. So this is the inner loop. When you write code like this, you realize that you're implicitly hand controlling one GPU. But hand controlling one GPU with a double for loop is easy. Hand controlling a cluster of GPUs is not possible, right? And so that is where you need a framework like this. Right? When you use a framework like this, then a single GPU situation just becomes a degenerate case. It will just not let you make mistakes. It just gives you a easier framework to do that. By the way, this is not the only one. For example, Hugging Face Trainer gives you the same facility. You can specify some of these things. But here the value of Ray is somewhat diminished, but it is still reasonably, there's enough residual value that once you get used to it, just use it. Similarly for the Hugging Face Trainer, once you get used to it, just use it. Right? So that is in favor of it. Now, when you are in inference mode, then the dynamics changes. So you have a GPU Let's say I'm just assuming this 4090 in both of these situations, GB. So what can you do? You can take a 7 GB model, a 7 billion model in 16-bit quantization. That will take about a 16 GB space. And you can shove now a lot of data, lot more data for inference. And once again, for these things, what happens is you have three choices: do it by hand, write everything yourself. Inference gets problematic because you have a REST endpoint that's taking in requests, or you have gRPC. So typical access to request is through REST, through gRPC. And now you have to manage batching, isn't it? You have to manage batching. For example, REST you may do using Fast API. Yeah. You can do gRPC. You will have to manage the batching and other things. Or alternatively, you leave it to one of these frameworks, Ray or Hugging Face, Inference, and so on and so forth, TGI, and so on and so forth. You can leave it to those, and they basically take the headache off you in such a situation.
Okay.
So
Asif, the question was more on the cores, right? The 26,000 or 16,000 cores that 4090 provides you. Are they being used optimally in this situation when you have one GPU? And are they?
Oh, yes. Yeah, they are, yes. See, that is so, okay, let me come to that thing. Whether you have one GPU or you have 10 GPU, the question of when a mini batch of data. So, okay, let me answer that question. That's by the way slightly different from our topic, but since you want that answer, so here's what happens. When you have GPU 1, G1, G2, GK, there are two kinds of sharding you can do, and this is again a pretty involved topic in distributed compute. See, you have data, and the data has to go through so many computes, 1, 2, 3, 4, 5, right? So many computes. So what you can do is you can do data sharding, right? So data sharding, data parallelization across the GPUs. But if there is only one GPU, you can't do that. Or you could do compute sharding, right? A different goes here, this goes here, this goes here. So in a multi-bank and distributed compute frameworks like Ray, what they give you is they give you data parallelism and compute parallelism, both of that, right? And by the way, PyTorch now has native support for all this, and then Hugging Face has support for all of this, and everybody seems to have support for all of this, right? So because everybody is trying to come up with an efficient data distributed compute framework. What happens when there is a single GPU? Now, that means we need to look inside the GPU. Guess what? The CUDA, each of these, that is exactly what the people who write the CUDA compilers and CUDA optimizers inside it, that's what they are doing. So when you have a PyTorch, the real hard part of the PyTorch code is to take that Python code, the data movement, bring it into the GPU and do exactly that inside the GPU. Does that make sense, guys? The same sense of a data parallelization and compute parallelization inside the GPU. What is the data? So is it efficient or is it not efficient is the question. The question is not whether there's one GPU or there are more GPUs. Whether it is efficient or not depends upon the kind of model you have and how well the machines are able to use the model. There was a recent study, I think, but it's, well, by recent, not very recent, I think I saw it 8 months ago. That research paper, in fact, yeah, things like that. For example, VLLM uses flash attention. You'll see that. There are many, many techniques. What people have realized that because there is data and compute parallelism, when you take data, it is brought into the core and brought back out. Like if you do matrix multiplication, the entire matrix, to you, it looks as though you're doing a matrix multiplication with a vector, something like that. In reality, that's not what takes place. What takes place is blocks of it are brought in because only blocks of the matrix can be loaded. Remember, these are tiny little cores with tiny little local VRAM, ability to compute accessibility.
Asif, I use something called nickel, NCCL. Is that what you're explaining, or is this you explaining? I mean, how they kind of scatter the data and how they manage all the GPU
Please say the word again.
NCCL, nickel.
Yeah, things like
Collective Communication Library. That's that's the library we loaded so that it's distributed across across the single GPU, but across multiple cores using CUDA.
that is right. See, the NVIDIA does give you these libraries to do that. And see, most of us don't care because we trust that PyTorch developers are in cahoots with CUDA, are intimately familiar with CUDA internals, and they are taking care of all of this. But yes, that is exactly what they do. You absolutely hit it on the head. That is why one of the hottest, actually, the topics and hottest topics is, people often call it model compilation, right? What do you mean by compile and what do you mean by execution? This is how it executes inside the GPU. How is the data sharded? How those blocks of matrix being passed and things like that, and they are moving in and out, and data is, so what is happening at the level of multiple GPUs is also happening at the level of the multiple cores within a GPU. All of those concerns, but it's just that different teams deal with it. Those guys who make distributed compute ML frameworks like the Ray makers, they usually don't worry about it. But the people who make frameworks like PyTorch, etc., they do worry about it. And one of the recent developments, if you notice, like people like Andrej Karpathy and some of these people, what they are saying is they are altogether abandoning these Python frameworks. They have begun to write, for example, a transformer, a GPT or something like that, entirely using the CUDA library. They're saying, hey, it is hard to reason inside the GPU. Let us use the code as close to the bare metal as possible and use that. And of course, when you do that, it's blazing fast and so forth. But see, now we are digressing from the point. But yes, you're right. If you look at what Grok did, GROQ did, they basically looked at this whole GPU and they said that, guess what? A lot of the thinking has gone because you're making a GPU which does both, and in which the CUDA and all these libraries, they are optimized to do both inference, the forward pass, but also the gradients and the second derivatives, or the quadratics. Manage it for Adam optimizers and so on and so forth. And it's very complicated. The storage of the data, everything is very complicated. Now, most of the time, so here's the answer to the question. Just as a normal CPU, inside the GPU also, most of the time is wasted in moving data back and forth between the near memory, the inside GPU memory, HBM, what is called high bandwidth memory, and the core itself, compute itself. A lot of the time is wasted there. And one of the reasons some of these frameworks, they try very hard to do things like VLLM, etc. They all try to optimize this area of the compute.
Can you touch a little bit on flops, Asif? Floating point.
Flops is straightforward. Okay, let me do that. FLOP. See, it stands for floating point operations.
I was just looking at the explanation you're giving in the parallel processing to see, why the latest computing is kind of measured based on the flops and stuff like that.
Oh, yeah, definitely. See, what happens is that every floating point operation at the arithmetic logic unit, right, is two registers. Register 1, register 2, right? And a binary operation, right? Sum operation. It is either plus, multiplication, etc., right? So it's a floating point operation because these numbers, in machine learning, the only numbers we care are floating point. Unlike most of general purpose computing actually is mostly integers. But in mathematics or in machine learning, all of these numbers are floats or floating points or decimals. Points are simply termed decimals. So you're adding, subtracting, multiplying decimals, right? So that and given two registers, that's all you can do. Or given one register, you can do a unary operation, add one, for example, or you can do a binary operation. That's about it. Right? Think binary operations and things like that. So each of those operations is a floating point operation. Now think about it like this. Suppose in a transformer, you send all of these tokens, T0, T1, T2, T, token K. You know that they will go through all these attention heads. Right? So let's just take one attention head, for example. One attention head here, A, right? And what will happen? It will cause every token to pay attention to every other token. Does that make sense? Right? So you will have lots of compute. So whatever the computes is, the attention head computes, let me just call it attention head. And let's take a very simplified version of a transformer, a single attention head, which has followed by some feed forward layer. In reality, this will be followed by another attention, right? And this will not be single, it will be multi-attention, right? It will go through multi-attention. It will go through feed forward network, feed forward network. What happens is that, think about what happens. Every single weight, the embedding vector, input embedding vector will be multiplied by W, K, WQ, WV, isn't it? So all of the weights here, you can count the number of floating point operations. It will literally be proportional to the size of these. And typically these are 64 dimension. So 64 dimension, and whatever is the embedding vector, let's say that the embedding vector is 300 dimension, right? So you have a matrix of this size to which you'll multiply this vector with. So you have a lot of floating point operation. After these attention computes, it goes into feed-forward network. Actually, feed-forward network is exactly where most of the computes takes place. People don't realize that feed-forward networks are dense networks. Every node is connected to every other node. So suppose this is 1024, 1024, and maybe let's take even, I'm taking 1024 because it's a nice, closer to 1000, 1024. You realize that you have 1 million here, 1 million here, computes here in just 2 layers of the feed-forward network, something like this, right? So, and every single, the signal transduction that will happen, the signal that comes out, vector that comes out, these vectors that come out, they have to do a signal transduction through this entire system. Means all of these things will add up massive amounts of floating point operations. I hope you see that, right? Each of these will contribute a massive amount of computes, and each of those are floating point operations. So roughly speaking, you just look at the number of weights and weights, right? At any given moment, any weight, Wij of layer L, will multiply something, right? And it will multiply many, always x1, xk, all coming xk, that feed into this, that feed through this, somewhere around that, right? Actually, no, I take that back. It is I. It will only go through I. This refers to only one, and this refers to wk, and let us say j of the layer L. right? So it goes through all of these computes need to take place. So that is it. The computes that happen inside a transformer and inside these things are bizarrely high, so that people today, there was a time I remember that million, like a million flops was considered, wow, so many million flops. Then it was billion flops. Now we talk in terms of trillion flops. And then we started talking in terms of p-flops, or petaflops, right? So we are now measuring GPUs and CPUs, etc. I mean, especially the GPUs in terms of T-flops and p-flops. So that's all there is to flops. Basically, machine learning is flops, all flops, floating point operations. Anyway, let's come back to our topic. I hope what I'm bringing home to you is that to reason in this environment is not easy. And any framework that simplifies all of this complexity from you and does the right thing, even if it does it imperfectly, and let us grant that current frameworks are somewhat imperfect, actually, and can be frustrating. Nevertheless, you don't want to do without them, isn't it? Does that make sense? Right. So with that introduction, now let's go and look at what does this give you? I said that if I had a class, where was my class gone? Yeah, if I had a client, and if I was talking of a class like X, and if I did not have to worry about all of the complexities, a framework could let me write this code and get away with it, isn't it? Now, there's a problem with this. You can't literally do this because this is a class. Python will just go instantiate the class. Does that make sense? So there is a way to say that it is meant for the framework. Don't do it locally. Don't do it inside the client. And basically, what this does, it says, just annotate it with remote, decorate it with remote. Add the remote decorator to it. It's very simple. Add the remote decorator to it. And then you don't have to worry where that instance of that class is living, right? What you will have to say is, instead of that, say X instance, X, little x is equal to capital X dot remote. Are we together? And instead of saying increment, just say X dot increment dot remote. Now observe carefully, what have you done? You're saying if you annotate this class, it becomes what is called an actor. It will somehow magically exist in a distributed environment, no matter where and how the requests are coming from. It will survive on a nodes safely, even if some nodes are dying and coming alive, right? And when you do increment, wherever it is, its value will automatically get updated. So let's say that you want to increment it by 10 more horses. It will take care of that. Right. Now, if you look at this sort of API looks a bit strange. What is this whole remote business? So here is an easy way to remember it. Whenever you think remote, right, just do this in your mind. In your mind, and again, pay attention. Look at this API. If I just erase the dot remote from it, what would it look? It would look like X is equal to X like this, and X dot that is what it would look, right? If I erased from both of this text dot remote, isn't it? And this code that you're looking at Does it look like a very local, nice local code? Right? And so this is your path to go between what you would locally do and what you would do in a distributed cluster using the Ray framework. Do you see the analogy here, guys? This is it. It's a framework that says first write your code locally, like in what it would look on as a simple Python program. Right. And just go, therefore, and add the dot remote in between. Just inject the dot remote everywhere in your code. So from an API perspective, well, it is not completely transparent, but it's about as transparent as you can get. Like as the cluster, the whole distributed cluster with all its complexity is about as hidden as could be. The only telltale sign that you're doing computes on a distributed cluster is the dot remote word. A small concession. Would you agree? Right? And so to read code, which is meant for the distributed compute, is very easy. In your mind, just erase the dot remote everywhere. Now, what can be done? You can say, hey, here's the thing. This is a class. It is maintaining state. But suppose I have a function, just a simple function, def greet, right? And if I greet, it should return. And suppose I give it some word or phrase, it should return. Let us say that it has the ability to French, since all greetings sound sweeter in French. Right? And then you return French greeting. Now think about this function. This function is, you don't want to decide how many instances, where is this function being run in the distributed system and so on and so forth. You just want to, and also convert it to French is not that easy. Most likely you're going to load a transformer, right? Using a language model, right? Or some method, I don't know. Convert it to something. Okay, let me convert it to not French and the language, to capital letters. Let me just say capital, right? And do something else and whatnot. Do lots of things, right? So now, how would you run it in a remote way? Once again, just say remote. It runs in the cluster. Right? Now, let us say that this takes, let us say, it takes 5 to 10 seconds to do. Well, greet is not something that should take a long time, but let's imagine that it's a pretty complicated thing. It takes 5 or 10 seconds to do, right? Then what you do is, the question is, what does this function return? When I call greet with a string, implicitly what happens? You block. In Python code, you call this function, you block. And what will you get? You will get result, which will be a str of the type str from the greet. Does that make sense, guys? Right, and let me be explicit about the return type. Str. You'll get a string. What happens in a distributed compute, and here's the fun part, and this is the only thing you need to remember. What the distributed compute says is that just go ahead with the computation. I'll give you something called a promise or a future, right? The concept is a future. You will get a future back. So you get result future is equal to greet. If you did greet.remote, remember, what do you do to make it into a distributed call? All you do the same is sneak in the word .remote between the function name in this box. In this space in between. Do you notice that I snuck in .remote here? The moment you do .remote, what really happened is the machine actually didn't give you a result. It might have chosen to if it was a quick compute, but what it gave you is a future. And so this falls under the category of something called asynchronous compute. In distributed compute, you want that. You basically say, hey, you got a result. By the time you actually need it, we'll give it to you. So somewhere down the line, suppose you need it, right? What you can do is you can say, there are two ways of doing it. You can say either call get directly on it, or if you have 2-3 futures. So let's say that this future is there, other future is there. Multiple futures have accumulated. What you can do is you can say array get and give it a list of all the futures that you want. You say that I'm going to wait now. I can't proceed till I have the actual value of these things. So what really happens is it gives the distributed system, let's say that this function is facing a lot of traffic, or there is a delay, or it's doing heavy computations. For whatever reason, there's latency. The machine doesn't block you, right? The distributed system doesn't block you. It gives you a future to reason with and move ahead. But when you actually need it, you can call for it and it will give it to you. It will say, all right, now wait. The moment you do get, what does get do? Block. It blocks you because it says, now I have to wait for all the computations to go through. But what is the beauty of this? Suppose you want to get 3 things done. 1, 2, 3. You could fire all of them one after the other. They will all get executed in parallel. And then you can ask for, you can say that, okay, here. So, it's a future is like an IOU. The distributed system is saying, I owe you. You keep collecting the IOUs, and then finally you say, okay, now is the time. I need all my IOUs to be in cached. Give me the actual thing, right? And so it will give it to you. Advantages are, obviously, asynchronous systems are always well-conditioned systems. They take traffic much better. They take load much better. More than that, they allow for much better distributed and parallelized computes. Third thing that it does is, and this is where I'll bring in the last element of today's session, which is the nature of how does Ray actually do it. So by the way, when you annotate a function with remote, what you just created is one more entity task. Right? So let's see what are the big guys we are creating. A future, a task, an actor. Where's our actor gone? We have hidden the actor somewhere. Oh, this was a task. Where is the class gone? Okay, remember, when you take a class, we took a class somewhere. I think we are scrolling past it quite a bit. Where is mine? Oh, here it is. It became an actor. You saw that, right? So a class, so here, what is the mapping? Let's do this. Class in a distributed environment, if you attach the @remote to a class, it becomes an actor. If you take a function and you apply @remote, it gives you a task. And when you invoke any of these to do something, the variables, right, which are the result of calling in remote function, the remote function always is a future. right? And future get will convert it into a actual value object, a result. This is all there is to, in a simplified way, to the core of Ray. It helps you reason in a distributed environment. Now, how does it reason or help you reason with respect to machine learning and so forth? I have not explained that. I will go into that. I've been speaking without a break. Do you guys need a break or we can continue? We can continue, right?
How about 10-minute break, Asif? You need a break.
Okay, all right. Let's take. So guys, let me summarize. The core of Ray is this, right? Classes become actors, functions become tasks, variables, right? If you call, when you, the return value are not variables, when you do the remote function call, you get a future. Future is a promise for something, right? And together they make a asynchronous. The big message is distributed compute framework core. That's it, right? With these ideas. And it takes a little bit of time to get used to the Ray core, the core of the Ray framework. Everything is built on top of it. But if you get used to this, it will be very, like, it takes a little bit of time to get used to it, to think in terms of actors, tasks, and futures. Right? If you have been used to asynchronous programming, then it's a little bit easier. But if not, it is a little bit counterintuitive, let's put it this way. It takes some getting used to. I would strongly suggest that you get used to it. It's a very powerful framework, and the Ray core is quite mature. Not perfect, but quite mature. It's very effective, and it really does work well. Everything is built on top. The rest of the Ray framework is built on top of the Ray core, and we'll go into the rest of it later. Let's take a 10 minutes break, and I'll stop the recording.